and we are looking at infinite limits. So what happens when x goes to infinity? And this can be a very important concept. We're wondering what happens as the x values get really, really big. Well, here we have a parabola. And if you draw your parabola off to the side here, maybe there it is. As x gets really big, we're asking what happens to the y values. Well, they get very big. So as x gets very big, the y values get very big. And we would say that the limit as x approaches infinity for x squared would be infinity. Now, depending on the textbook, and I think your textbook might be one of the ones that says, hey, wait a minute, infinity is not a number. So in the textbooks, some textbooks will say limit as x goes to infinity of x squared does not exist, okay? But we're going to want to be a little bit more specific. So we'll be writing answers like if it goes to positive infinity, we'll write positive infinity. If it goes down forever, we'll write negative infinity, because it gives us more of a sense of what's happening. So a lot of these you can solve if you think about the graph, but you can also just sort of solve them with mental math. Does it make sense that if you put a very big positive number in there, you would get a very big positive number? Like if I put in 1,000, 1,000 squared is going to be positive and it's going to be very big. Here's a line, negative 3x minus 5. Put a big number in. What's going to happen? Are you going to get a big positive number or a big negative number? So we're going to say that that limit is negative infinity. And infinite limits, sometimes they'll say as x goes to positive infinity, sometimes they'll say as x goes to negative infinity. So in this third example, we're imagining what happens if we put in a very, very large negative number. Well, that very large negative number will get cubed. When you cube a large negative number, it will be large. Will it be positive or will it be negative? Negative. So this one, we would say, tends to negative infinity. If you have an exponent bigger than 1, so r could be 2, could be 3, could be 2.5, anything bigger than 1, does this make sense? That if you put in a very large number and the power is bigger than 1, power is bigger than 1, make things get bigger and bigger over time, that would also go to infinity. So what we're trying to sort of do here is mental math with very, very big numbers and see whether or not they're still very big numbers or what happens with them as we go. Now, 1 over n. If you think about graphing y equals 1 over x, because the variable doesn't matter. It could be x goes to infinity, n goes to infinity, whatever letter they have going there. If you graphed 1 over x, you would have an asymptote here, an asymptote here. Do you remember this graph? That it would look like that? Yes. Why does it have to be above 1 for r? Because, okay, that's a good question. Let's go back to here. So this question is here, if r is bigger than 0. So even like, if r is a half, right? That's a square root. And as x goes to infinity, for a square root, that would be bigger and bigger and bigger as well. So is there a value in there? Should this be r bigger than 0 all the time? The only problem with saying r bigger than 0 is that when r is equal to 1, it would still go, because it would just be x there. That would be fine. So sometimes r equals 1 is a problem because an exponent of 1, but that would still be infinity, right? So is there any problem with any values bigger than 0? I don't think so. I think it would work for any value of r. Because as soon as you get, if r is between 0 and 1, like if you think about what does a third mean as an exponent, it's a cube root. And even as x gets bigger, even if you cube root a bigger number, it keeps increasing as well. So this might have just been a typo. For sure, when r is bigger than 1, it works, but I believe for r is bigger than 0, it would work as well. Okay. And obviously, r equals 0. Anything to an exponent of 0 is equal to 1, then that one wouldn't work. So if you're looking at a 1 over x graph, and you're imagining the x values getting bigger and bigger and bigger, what does the graph start to approach? It gets closer and closer to 0. And if you think about values, right? If I put in 100, 100th, pretty small. If I put in 1,000,000, 1,000,000th, very, very small. The bigger the number I put in, the closer and closer this gets to 0. And so what we're going to look towards is this concept. If you're dividing by a very large number, whether it's positive or negative, can you see that if n went to negative infinity, the same thing would happen? It would still approach 0. So when we have an expression like number 5, n goes to negative infinity, meaning this number on the bottom is huge, a huge negative number. 1 divided by a huge negative number will be very, very close to 0. And so this limit is just 5. So I think something kind of strange is happening at this moment because we're dealing with infinity and huge numbers, and yet do the results kind of feel like common sense so far? Like it's not like, whoa, I can't imagine this. Even though you're dealing with infinite numbers, they seem to be making sense. And in fact, whenever you're dividing by a large number, 1 over n to the anything, and here it is, r is bigger than 0, so it must have been a typo from the last one. 1 over any value of n to any power, as long as it's positive, is going to equal 0. So that's going to help us as we get into a few more complicated questions where we're going to have this as a strategy. Now, in grade 12, you graphed rational functions like 2n plus 3 over n. And in grade 12, you would have said, okay, there's a non-permissible value, n can't be 0. That's going to be a vertical asymptote. But this was also something when you graphed, it had a horizontal asymptote. Now, in my classes, I would always say if the degree of the function in your numerator was same as the degree of your function in your denominator, if they're the same, then you can basically ignore the 3 and your horizontal asymptote is whatever you get when you have 2n divided by n, which is 2. So this graph has a horizontal asymptote at 2 and a vertical asymptote at x equals 0. And if you wanted to plot certain points in here, you could plug in values. Like, for example, if I plug in 1 for n, I'd get 1 comma 5. If I plug in -1 for n, -2 plus 3 is 1 divided by -1. So I could find some points on my graph rather easily. Now, from the graph, we can see the answer from this, right? As n goes to infinity, what does our graph get close to? It gets close to 2. Okay? And sometimes I teach it the same thing that I teach to grade 12. If the degrees are the same on the top and the bottom, in other words, if the highest power on the top is a 1, the highest power on the bottom is a 1, if they're the same, you can just look at the coefficients, 2 divided by 1, and get the limit. If we want to formally show our work, we divide an n out of the top so that that n simplifies with this n. And then your limit just becomes the limit as n goes to infinity of 2 plus 3 over n. Well, 2 plus 3 over n, this part, anytime you're dividing by infinity, that's going to be 0. So your limit is 2. However, as a shortcut, right, if you did this in your head and just said it was 2, I would be fine with that because you have the same degree on the top as you do on the bottom. Really, that plus 3 doesn't matter anymore. Like, once numbers are really, really big, plus 3 doesn't matter, right? If you're trying to go home on the bus from school and you have 25 cents and you have an option to someone could give you plus $3, makes a huge difference. You don't have enough bus fare compared to you do have enough bus fare, right? But if you're, you happen to own Amazon and someone's like, oh, here's $3, you're like, no, it's okay. I think I'm okay. I don't need an extra $3. It won't affect my bank account very much when I've got billions of dollars. So when n gets very, very big, that plus 3 is sort of no longer even in the picture anymore. And that's why the limit can just be seen as being 2. Mathematically, though, if you want to show your work, because this is an example of an infinity over infinity limit. Technically, if you plug in a very large number in the top, you get infinity. If you plug in a very large number on the bottom, you get infinity. And infinity over infinity isn't clear what that answer would be. In this case, it's 2. But we can make other cases where it's 5, 7. So because that's unclear, this is the proper technique to show that it cancels, because you will get things that you can say, well, if we use the idea that this is equal to 0, then we can solve it. All right. So if you didn't show your work, can you see what the answer would be? What's the highest degree in the top? An n cubed. Highest degree on the bottom? An n cubed. So if you ignored everything else, you get negative 3/8 as an answer. Because when things get really, really big, it doesn't matter that you have n squared in there. Because the n cubed is way more powerful than an n squared, even though n squared is very powerful to begin with. Now, if we showed our work, you would factor out the n cubed out of the top, and you would factor out the n cubed on the bottom. That would allow these things to simplify. And then, as n goes to infinity, anytime you're dividing by a very large number, those will be zeros, and you would just get negative 3/8. So again, if you see that the degrees are the same on the top and the bottom, then it's easy to see what the answer is. Where things get a little bit tricky, we get in problems like this one. What's this going to equal? N gets very, very big, and you've got negative 1 to the n. Well, if it's a 1, this would be negative 1. If it's a 2, this would be positive 1. If it's a 3, it'd go back to negative 1. If it's a 4, it'd go back to positive 1. So if we just look at the whole numbers, can you see that it's flip-flopping between negative 1 and 1? And sometimes when they have limits like n going to infinity, sometimes that's an implication that you're only looking at integers. They like to use, if they said limit as x goes to infinity, sometimes that implies more like we can include any numbers. And the problem with including any number is that would include fractions. And if you put a half in for a fraction, a half would be a square root. That's not even possible. Okay? So this one is problematic because if you just look at whole numbers, it flips between negative 1 and 1, negative 1 and 1. And so here, because it doesn't go towards one value, it switches between different values, we're going to say that the limit does not exist. Because for a limit to exist, just like the asymptotes that are there, it needs to be getting closer and closer to a single value. And this one's oscillating between positive 1 and negative 1. Okay, do some mental math thinking on this one. Does this go to a value or does it not exist? Well, if you think about the numbers, you go 1/2, then 1/4, then 1/8, then 1/16, then 1/32. What's happening to our numbers on the bottom? They keep getting bigger and bigger and bigger. And so this limit, as n gets very, very big, those fractions would get very, very small, and we would say that they're equal to 0. Now, you've actually used this concept in grade 11. You probably weren't ready for it. I'll pull up a grade 11 formula sheet. Do you remember do you remember this formula from grade 11? And do you remember this formula from grade 11? Ooh, the first formula you ever had the infinity sign in. What unit was this from? Sequences. And geometric sequences, and the sum of a geometric sequence. So you had a not very nice formula if you just added up the first 20 or the first 30. But if the absolute value of r was less than 1, in other words, you had a fraction between 0 and 1, either positive or negative, then the formula turned out really nice if you went to infinity. Because what happened is if n goes to infinity, here this 1 minus r to the n is like this. It just became 0 in that formula. And so your teacher would have said, we're kind of doing a limit here without using the word limit or any notation that showed it. But once this becomes 0, then the formula simplifies really nicely to the infinite formula. What happens when you get close to dividing by 0? So I want you to think about this one. And I want you to also think about this one. Are they same? Are they different? I'm going to tell you they're different, which is you're probably initially thinking they're the same. I'm going to tell you they're different. I'm going to tell you one of them has an answer and one of them does not exist. And if you think about the graph of 1 over x, there it is. And you think about earlier when we talked about a limit, in order for a limit to exist, you needed to approach from the left side and from the right side, and it needed to approach the same thing. So when I come from the left side, so if I do the limit as x goes to 0 from the left side, can you see that it goes down forever? We would say the limit as x goes to 0 from the left side is negative infinity. And again, some textbooks will say it does not exist here, but we will say, yes, there is a limit. It's equal to negative infinity, because if you go from the left side, we know that our graph keeps going down forever. But if we go from the right side, it keeps going up forever. So from the left side, it's negative infinity. From the right side, it's positive infinity. This limit does not exist. But the second one does exist, and we would say that it's equal to infinity. Can you see that no matter if you put a positive or negative number in, when you square it, it's going to be positive, and dividing by close to 0 is going to give you a very, very big number. But I would say this is one that I would have made when I was in university. I made mistakes on this one all the time because you get a concept that if you divide by a very, very small number, you get a very, very big number, which is true, but you have to be careful that sometimes it's very big positive numbers, sometimes it's very big negative numbers. So the first one, because the left side limit and the right side limit are different, we would say doesn't exist. If you draw the graph for 1 over x squared, oh, and you guys all took grade 11 math during the pandemic, right? Nobody's pre-pandemic grade 11. This was the unit that they skipped in grade 11. Grade 11 teachers, when this is taught in grade 11, we call this the volcano graph. Doesn't it look like a volcano? Asymptote spewing lava out of the top and everything. But when we look at the graph of that one, you can see that they're both approaching infinity in the same way. Okay, I have some infinite limits for you guys to try on a handout here, so I'll hand those out